on Monday morning. Yes. All right. So to recap, because we've now lost the first few moments, pentagram is... Yeah, that'll go away in 30 seconds. If I don't, it just destroys something. So the idea is we have a pentagram. We want to add 2 more lines so that we have exactly 10 triangles. And we want to find a good way to search through the space. So this is inspired by a lesson I did on lines of symmetry. So if you have a figure, the definition I heard for line of symmetry was you draw a line through the region, and then you can fold it so that the 2 halves fold together. And if you have something like that, that's called a line of symmetry. Has anyone done this in any of their classes? Okay, what grades?
High school.
I'm sorry? High school?
Yeah.
High school. Okay, geometry? Yep. My feeling is this could be done to some extent in elementary school.
Do you mean regular, anything about symmetry?
Anything about symmetry.
I do it in 4th grade.
Yeah. So talk about when you have an object and when can you fold it such that the 2 things become the same. We either have a way for you to... All right, found a place. Excellent. All right, so what do you think the simplest first shape is that we should look at for lines of symmetry? Triangle, right? Can't do, a figure with just 2 sides. It's not going to close off. So the simplest thing we can do is a triangle. So I'll start off with an equilateral triangle. What are the lines of symmetry? Yes?
Top to bottom, from the top halfway through the point.
Okay, so we have this one as a line of symmetry.
Then the same from
Really from any vertex.
Okay. And they should all meet if it's well drawn over here, if it's an equilateral triangle. Are there any other lines of symmetry? Okay, so I think at a very early age people can figure out that these are the only ones. But of course this is not a proof. We need to find a way to prove that there are no other lines of symmetry. The other thing is it's very easy to extract additional facts about lines of symmetry that may not be true. So let me draw next to this the next simplest figure, a square. And so building on a resounding success with the equilateral triangle, what would be the lines of symmetry for the square? Diagonals. Right. And so this is one of the real dangers is when you start off with something like this, you might have in your mind that a line of symmetry has to start in a vertex. But we could also have a line of symmetry coming down like this or coming down like this. If I had other colors, we'd be thinking of Great Britain right now, but okay. So we have these as our lines of symmetry. Is there anything else? No. And so again, one of the points is choosing really good examples so that you realize that this example has a certain property. All the lines of symmetry start in a vertex. It's not necessarily the case that you always have lines of symmetry starting in a vertex.
But also, those lines that go in the vertex are also going to the midpoint of the opposite side. So you always have lines of symmetry coming from the midpoint and from the vertex.
Okay, so good. So this then allows us to go back and look at the lesson we've already said, and what can we extract from this? And so one of the similar things, as you're saying, is that maybe you either go from a vertex or go to a midpoint of a side. And so could we isolate that as a theorem? Start at vertex or end at midpoint of side. So can we prove that conjecture?
It would be more than that, though. You could start at the midpoint of the side and go to the midpoint.
Correct, but then you would at least end at a midpoint of a side.
Talking about this.
What I'm saying is one of these always true for a line of symmetry. Do you either start at a vertex or end at a midpoint of a side? And of course, if I just choose to go through things backwards, I can now say I'm ending at the midpoint or I'm starting at the side, whichever way I want. So maybe a better way of phrasing this is you include a vertex or you include a midpoint. So, yep, include vertex or include midpoint of side. Must one of those two statements be true? They could both be true, but here's an example where I don't go through a vertex. This is inclusive or. When I was in college, I almost got into trouble in a logic theory class. The professor gave us 10 statements, P and Q implies not P or Q, and the instructions were state which of the following are true or false. And this is a logic theory class. And I almost wrote all of the 10 sentences are truth value determinable. They are all true or false. You used the inclusive or, you're a moron. This is a logic theory class. She told me afterwards that she would have laughed and flunked me. And I'm not sure she could have gotten away with that because it's a logic theory class. She used the inclusive or. So here, it could be the case that both are true, but I'm claiming that at least one must be true. So do we feel that at least one of these two statements must be true?
Yes.
So far. And so the question is, how? No, we've got 2 data points. I mean, that's pretty good. So much.
Yeah, you did that, or not just the adding.
Yeah.
But we also look at regular polygons.
So right now we're only looking at regular polygons.
Two things you have vertices and you have sides. So
Correct.
you have to bisect one or the other for the symmetry.
Right. So one thing is we're folding onto each other. So a line of symmetry you have to fold. So if I cut through a side, I either have to fold that side onto itself or I have to fold it onto another one. And so if I'm going to be folding it onto itself, I've got to be splitting it in two. If I'm going to be folding it on something else, I've got to be going through a vertex. So I think that would be a pretty good quick proof that at least one of these two statements must be true if we're looking at lines of symmetry in the plane. Another thing which is really nice is when I have a line of symmetry, I have to split the area 50-50. Also, area is 50-50. Because I'm folding it onto itself and I'm completely covering, so each of the two regions must have half the area. So when I'm trying to figure out what are the possible lines of symmetry, we now have a lot of things to help us going through the list. And this is, I think, one of the difficulties people have is methodically going through all the possibilities and not missing anything. It's very easy to just draw the possible candidates, at least the candidates you think are the real legitimate ones, and miss some of the more subtle ones. And you want a very good methodical way of going through everything. Because while it's not too hard to find lines of symmetry for something like this, when we get to the pentagram problem we mentioned a little while ago, it's much harder to figure out how to put the lines so that we get exactly 10 triangles. In fact, somebody thought I might have even meant to write 9 rather than 10.
So do you want you in the video?
No. As long as the math is in. The math is far more important than I am. Eventually I'm trying to get like Arnold Schwarzenegger or someone to, play me, but we'll see how well that works. All right, so let's take a regular hexagon. So what would be the possible lines of symmetry for the regular hexagon? Same rules. So we know we've got to start in a vertex. So if we use that, if I start in this vertex, the only way that will work is if I go to the vertex down here. Otherwise, I'm not going to split into 50-50. So I've got to go to the opposite vertex. The other possibility is if I start at a midpoint, I've got to go straight down. So in this case, the only solutions are going to be the lines like this, and the lines, let's see, like this. If we hadn't proved all those nice results before, there's another way we could have attacked this problem. And this is what's going to be useful for the next bit when we start looking at the pentagram. We're trying to find lines of symmetry. We're trying to find ways to put down the lines. So the question is, what is a good way to start going through the space? To me, this is related to, in geometry class, how do you know where to put the auxiliary lines? When we did the proof of Pythagoras, to me the hardest part in all of these proofs is you draw an auxiliary line. I can follow these proofs if I'm given them. If you give me the proof, I can go from line n to line n plus 1. But if you then ask me, what's line n plus 2? I don't know. But I can follow the argument as it's being given. So the question is, how do we find a good way to methodically look at possibilities? How many places do we have to draw a line of symmetry? Well, if we forget we don't have the proof of our conjecture. Anywhere. So how many possibilities are there initially? Infinitely many. It can go through the center, it might not go through the center. We have infinitely many. That is a lot of things to check. So we want to try to narrow it down a little bit. Without loss of generality, I claim that it's enough to consider lines that intersect here. Let's think about it. The line better intersect our region somewhere. Okay? If it doesn't intersect our region, we're in trouble. There's no way it's going to be a line of symmetry. It's got to intersect. This region is very symmetric. And so I can just keep rotating it. I can flip it so that this is the same as this. By rotation, it's the same as all of them. So I just have to look at what's going on through here. So now what I can do is for each point on this line, I can now look at all possible lines I can draw from this. And I'll have infinitely many. But for each point, I can now very methodically look at the possible candidates. And then we can start to use some of the ideas we had before to cut down on the possibilities. So one possibility is I can use the fact that it has to be equal areas. That's a really nice thing to use. The only way it can be equal areas if it then goes to the corresponding point down here. And we'll see if we go like that, there's no way we're going to fold it and have it match correctly unless our point is either here or here. So this just becomes a way to go through all the different candidates. And to me, this is the lesson I would want my students to get from something like this. I don't really care too much about lines of symmetry, but I do care how do I go through a whole slew of spaces. Far too often I see my students basically paralyzed with fear because they can't see the solution to a problem, so they don't start working on it. And they just have this blank piece of paper, and they won't attack it until they know a way that will work. And what I want them to get out of something like this is, how do you methodically go through the possible samples, the possible solution space in a good way to find all the answers? In terms of applications, why might we care about something like this? Well, we talked about tic-tac-toe last time. And so, I didn't mind that the conversation veered a little bit, but in terms of how you analyze all the tic-tac-toe games, this is a great example of this idea of lines of symmetry, and saying we can reflect the games and we can really reduce the number of calculations that have to be done. Other things, we were traveling again, and I again forgot to bring my son's plane pamphlet. I'll take a picture and post it. But if you think about how planes are designed, one of the big things now is planes have wingtips. And so, why do they have wingtips like this? Why are planes symmetric? What does this stuff do in terms of how well things travel, how air flows? And so you can start thinking about applications as to why might you want to build things with different kinds of symmetries. Rubik's Cube is another great example of fun with symmetries. Okay, any questions on the hexagon? On a side note, I spent over 2 hours yesterday dealing with airlines that had canceled my flights for some upcoming travel. It was useful to have a 7-year-old who was obsessed with airplanes and airports because he could tell me where the hubs were. And that was extremely useful. So Cameron, if you're watching this years from now, thank you.
Take other calls, like I call them.
Yeah, I was going to say, if you have questions, right now he's not so happy with United and USC, and I don't mind if that's recorded. He's really interested in people who want to fly like Delta. All right, so here is the pentagram. And the game was we want to draw 2 lines to divide it into exactly 10 regions. Okay? Now, if you think about this, there's a huge number of possibilities. There's infinitely many ways to draw 2 lines. And if you want to get even worse, it's infinitely squared because we have infinitely many traces for the first line times infinitely many for the second. Do the 2 lines have a common point that they radiate from? It's not clear. You can break it up into 2 cases and hope that they do. Yes?
You said 10 triangles before, and then you just said 10 regions.
I'm sorry, 10 triangles. Sorry, 10 triangles. Sorry, 10 triangles. And then we're not counting something giant like this giant triangle here as a triangle. If you want, imagine that after you draw your 2 lines, we cut the region among all the lines. And so we wouldn't have this giant triangle here. We would have just this one, and a pentagram in here. So we need a good way to try to use symmetry to attack this. Otherwise, this is a very poorly planned lecture. So how can we cut down on the number of possibilities for drawing our lines?
Either start at the vertex or start at a midpoint.
Okay, so one thing is, does the line have to go through either a vertex or a line segment? So which line segments do we have to worry about?
We can reduce it by using one leg of one of the outer triangles.
I'm sorry?
Can we look at just one of the legs of the outer triangle?
Okay.
Just take
Are you saying drawing something from in here, or?
Yep.
Okay, so the problem is we don't necessarily know that we're going to go through a vertex.
Right.
But we do know we have to go through at least either a vertex or a side.
Right. So from the vertex of the triangle all the way to the
Right. So what I would say is,
that whole.
is this whole thing over here, we know we have to cross this at least once. Right? You know, again, if we never hit the figure, we're not going to do it. We've got to hit the figure. And so one possibility is to say, well, look, let's choose a point of intersection here and draw a line from that. And that will give us our first line. The other way to do it is I could say by symmetry, I can look at the location of the first vertex. And I have to draw a vertex somewhere in this region. Because again, by symmetry, I can reflect this over to here and then translate it down. And so I either choose a vertex somewhere in this region, or I choose a point on this line, and then I draw my line from that. The reason I might want to choose a vertex is say, let's assume my two lines share a vertex. Well, now I have to start worrying about, well, where do they share the vertex? Do they share it externally or internally? And now we want to start going through all the different possibilities of where can we put things. So did anybody have any good ideas that got a lot of stuff? Or some ideas that did not get a lot of stuff that we can say, this was a promising idea and it did not pan out?
You can get 9.
You can get 9. So what was one of the ways you tried to say, well, look, this would probably be a good first attempt for drawing my first line?
Hitting that midpoint of that line there.
This one?
I'm sorry, the midpoint of the red highlighted segment.
Okay.
Going down through the vertex.
Going down through here?
Yes.
Yes. So this is one of the first things I tried, is if you come down like this, it divides this into 2, it divides this into 2.
And then if you do the other side, then it gives you a quiet exterior.
And if I do the other one over here, I can get 2 more over here, and I can look where these would intersect, but it would not be a triangle.
Yeah.
And so that would get us 9. So this is not a bad first move. It gives us 2 more triangles, but it doesn't give us much to play with. So one possibility is to think, what could we do to maybe maximize the number of triangles we get on the first turn?
You can make triangles out of the center region.
So one is to try to make, so one thing is to try to make triangles out of the center region. Right now we have nothing from here. And when we do this, yes, we've added 2 triangles, which is good, but we've added them from places we already had triangles. So in terms of a strategy of trying to go through this is to try to think, where are the lines the most effective? And by going through like this, we're adding triangles, but not, well, you didn't technically pass a note, so you're not in trouble. So can anybody think of a good way to draw a line in the middle that will get me a lot of triangles?
Do the star tip, like an altitude from the
From here coming down?
or the triangle you're starting in. You've already highlighted. From that
Okay.
tip,
From
the altitude, yeah.
So if I do this, this gets me 2 here, but it gives me nothing here. And again, sometimes the best thing to do globally is not necessarily to do the best thing locally. But what's the most number of triangles we can add with one line?
Well, what if you took the original line that we just got rid of and
Right.
shifted it just a hair to the right?
Yes, I like that. So if we shift this just a little bit to the right, a little bit drunk. So if we do it like this, we've created a new triangle here. We've created a triangle there, we've created a triangle here, and we've killed triangles in these other places.
We gained 1.
We gained 1, but we've created some pre-triangles. And so maybe we can then draw the next line to help fix the stuff over here. So now we've got 1, 2, and 3. So we've got a little triangle there as 3.
Or your original triangle, or your original line.
Now the other thing is, in a lot of problems like this, you have blinders on and you add constraints that are not really there. Where are we getting our triangles from? In everything we've discussed, where are our triangles coming from?
So far, they're all on the inside.
They're all on the inside. They're all coming from dividing up the region. Right? So it's so easy to put in these additional constraints on a problem that are not there. And again, that's one of the things I really like about this. Where else could we get triangles? On the outside. So we could maybe get a triangle from in through here and a triangle from in through here.
Can you extend any of the existing lines?
No. Nope. I don't know why, but... So now using something like this, we could try to draw another one coming down. And so now if we do something like that, we got a triangle here and here. And these are absolutely free triangles for us. And so now if we look, we have 1, 2, 3. We add 1 here is 4, 5, 6, 7. And there's 8, 9, and 10. Right. So there's the 10 triangles. Okay. So again, this is a problem you can give to people very early on in their careers. But there's a lot of stuff going on in the background as to how you would go through and figure this out. To me, it's also the blinders that we have to really take triangles outside. We're not going to get it by just dicing things up on the inside. The other thing is the initial region is very symmetric, but the solution is not. And that's a really nice thing to see, that you start off with something that's symmetric, but at the end of the day, the final product is not symmetric. Okay. Any other questions on the pentagram? Okay, so I want to do one more thing just related to lines of symmetry and then just end the unit. I'm using the high quality super recording, and so I can't lecture for too long without it overrunning. So a couple of us were talking before class started today on sequences. And so somebody gave me the sequence 1, 2, 3, 4, what's next? And your instinct should be 5, 6, 7. But it was giving, yeah. And so Mark said, but it could be just beats in the music. It could be 1, 2, 3, 4, 1, 2, 3. You know, we don't have enough data, but we often start to extrapolate. So one of my favorite sequences is 1, 2, 4. So somebody has to say what I'm 8, right? But it's actually 7, right? I'm sorry? I'm going to leave the next one as a homework problem. But I will say a homework problem. This is the age of Google. This is not a hard homework problem. Actually, there's something called the OEIS, the Online Encyclopedia of Integer Sequences. And so if you just Google OEIS and go there, you can plug in the first couple of terms of a sequence, and it will tell you all the candidates in its database that have that as either consecutive or just somewhere in that order. It is a phenomenal site. The Online Encyclopedia of Integer Sequences. Okay? The only encyclopedia I regularly read. Okay? In addition to listing the sequences, it will list known properties, it will list references. You know, when you input the Fibonacci numbers, it will give you all these identities about them. It's an absolutely wonderful resource. And so if you put in 1, 2, 4, 7, you will eventually find the sequence. So, poorly drawn, but, oh, I'm sorry, it was just deflated a little bit, sorry. All right, so we have a circle, okay? How many regions? 1. That's the first term of our sequence. Now I'm going to add a line. How many regions can I divide the circle into if I add just one line? 2. And in fact, no matter what I do, as long as I cut through the circle, I will have 2. Now, let me add another line. What's the maximum number of regions I can divide it into? 4. Now, I could be stupid and I could go like this and divide it into just 3 regions. But if I want to see what's the maximum number of regions I can do, I can do 4. So the sequence is the maximum number of regions you can divide a circle into, given n cuts. And so I hope somebody will at least order a pizza with me so we can have a large pie and we can actually play this game. And that might help Henry justify the expense. What if I now add another line? How many can I divide it into? Probably at most 7 because of what I'm writing. So if I go through the middle, how many do I get? 6. So can we do better than going through the middle? Don't go through, yes. Essentially, well, if I do something parallel here, cross 2 lines, yeah. With the almost probability 1, you will win. So if I start off with 2 lines like this, if I choose a point here and then I choose another point at random, odds are it will work. And so if I go like this now, it's 1, 2, 3, 4, 5, 6, 7. And so that will divide the circle into 7 regions. So again, this becomes a very difficult problem as you go further. Now, let's say you have another line. What's the best you can do? I think 11 is the answer. I'm not positive. Well, it's 11. It's 11 if are you doing it from this?
Yeah, oh, I see.
So again, I am not a fan of Joseph Stalin by any means, but the statement sometimes you take 1 step backwards to take 2 steps forward. Maybe the best way when you have 5 lines is not to start off with the best thing with 4 lines and then add another line. You would hope that the best thing you could do is to take the best thing here and then do the best thing you can there. But this becomes a very interesting problem, and I think this is a great thing to give students to play with. So this is basically all I want to say about lines of symmetry. In terms of applications, you've got airplanes, you've got tic-tac-toe, you've got all this game theory. You have methodical ways of looking through what's going on, trying to find a way to search the space when you're not sure initially what you should do. And so many times people just freeze when they're given a new problem where they don't know exactly what the answer is, to try to give people a clue. This is how you can start methodically searching through the space, and eventually you will find everything. And you will know that you found everything, and not just guessing and inspecting.
So if you have a line that goes through more than half of the spaces, is that what the plan is? Because then you're dividing them into? Or
So in some sense, if I drew something over here that looks initially good, divides those into 3, that would get me up to 10, but they've got an 11. So what's the maximum? We want to divide we want to divide 4 of the spaces. Now I've got 2, 1, 4, and 7. So if I draw a line like this, now I would add 8, 9, 10, 11.
You could always divide more than half the spaces in half.
Only if you choose your earlier line very carefully, so you can intersect all of them.
Right.
Subsequent line placement.
So the next move, you have to go through 10 regions to cut that, no, 5.
5 regions.
6, sorry.
Right.
1 6, yeah. Or at least 6. More than 6.
Right. And so this is where now,
If you cut 5 in half, then you add 5.
this is now where it starts getting tricky. And how you start to write everything. Okay, so let me hit the stop right now.